So last tutorial we talked about this equation and those consequences of conservation of volume in phase space. So today we're going to talk about two subjects. So the first, we're going to talk about ensembles. So those are mostly stuff that you already know, but it's kind of an introduction for the next tutorial that we're going to talk about quantum ensembles. So this is just so you have everything in mind. And we're also going to talk about the concept of ergodicity and about mixing, which is, I guess we talk now with Vividor, and how it seems to contradict what we did in the last tutorial, but it's actually not. So we're going to have a lot of fun. So let's start with ensembles. Okay, so I'm going to put everything in like a table form, so it's really more convenient to keep track. So we have basically three types of ensembles. Technically, there are kind of more, but for us there are three. So the first one is the micro-canonical, then the canonical, and then the grand canonical. So you talked with Vido mostly about the first two. We're going to talk a little bit about the third one. So I'm going to put everything in the table, and then I'm going to explain a bit more about the grand canonical part. Like we're going to you'll see. So okay, so when we talk about ensembles, we basically talk about the statistics of the system. So the ensemble defined by a few main characteristics. So one thing is the constants. So for example, when we talk about the microcanonical ensemble, the constant is going to be, first of all, the energy, which is the most important one. So the microcanonical basically describes a completely closed system. So the energy is a constant. The volume is also a constant. It's always going to be constant, but I'm still going to write it. And the number of particles. So because the system is closed, there's no place the particles can come from, so this is a constant. The second quantity that we are looking at is the probability. So we have some, let's call it Pi. This is the probability to be in some state I. So, in the case of the microcanonical ensemble, we have constant energy. So all of the states that have the same energy are equally probable. So the probability to be in some state I with some energy is equal to 1 over the overall number of states that have the same energy. So this is number of states with energy E. Okay, and the last, that's kind of related to the probability is basically normalization. Or we sometimes call it a partition function. So you usually know partition function from the canonical ensemble, but in the case of the micro-canonical ensemble and the grand canonical ensemble, they kind of have different names. So in the micro-canonical ensemble, this is just the overall, the overall number of states in the system. So this is also going to be omega of E. So this is like, that's where this probability comes from. And we're going to see for the other ensembles what this is going to be. So this is for the micro-canonical ensemble. Now for the canonical ensemble. So the canonical ensemble, now the system is not closed. We connect the system to a heat bath, so we allow fluctuations in the energy. So now the energy is no longer going to be a constant, and instead we're going to have a constant temperature. So the job of the heat bath is to maintain a constant temperature in the system. So we have instead the energy, we have constant temperature, the volume, and number of particles still constant. Now, the probability to be in a specific state I is going to be the weight by, so we have an exponent of minus beta EI, where beta is the inverse temperature, so this is 1 over kBT. T is the temperature. So this is the probability to be in some certain energy state I.
Divided by Z.
Yeah, so this is without the normalization, but yeah, let's set the normalization to be consistent. So normalization, also known as a partition function, is Z, which equal to the summation over all E minus B beta EI. We sum over all the possible energies. So now the energy is a variable, so we sum over all the possible states. So this is normalization because this defines all of the possible the volume of the space that we have. So this is why here we have the total number of states. Okay, now for the grand canonical ensemble. So now, in addition to the heat bath, we also connect the system to a particle bath, which means we allow particles to move in and out from the system. And so now the number of particles is not going to be a constant, and instead we're going to have a constant potential. Chemical potential, sorry. So instead of M, we're going to have mu, which is chemical potential. And we're still going to have V and T, because the heat bath still exists. So now when you look at the probability to be in specific state, so I'm going to write it, you maybe saw it at some point, but I'm going to write it and then later we're going to prove it. So the probability to be in state I is 1 over the partition function, E minus beta EI minus mu n. So we have now two variables in the system. One is the energy, and one is the number of particles. So mu is a constant, beta is a constant, and we have two variables. Which means that when we write the overall normalization of the system, we're going to have two summations. One over, so the inner one is over I, which relates to the energy as before, and the other one is over all of the possible number of particles. So we have E minus beta minus mu n. those are all the ensembles. So now what we want to do is kind of quickly go through and then try to prove this formula for the non-canonical ensemble. Can I erase that? Okay, so we are going to start with the entropy. So in the most general way, the entropy is equal to minus Boltzmann coefficient, and then we have a summation of pi, and then log of pi, where I is some state. This summation can be anything. So, what we want to do is to find we know that the entropy is equality that quantity to get to a maximum point. So we want like minimum energy, maximum entropy. So we want to find maximum for this function under 3 constraints. So the first one is normalization. So we look at the probability p. So the sum over all pi equal to 1. So this is normalization. The second and the third one are kind of trivial, just the definition. We say that the average energy, so this is sum of EI, PI, so this is just the average energy is equal to the average energy. And in a similar way, the average number of particles is equal to some average number of particles. So those are numbers, so it looks like a trivial definition, but because those are numbers and those numbers going to appear later in the formula, we write it like that. So I'm going to write E and N, so I don't have to write the brackets all the time. So those are the 3 constraints. So I assume you remember Lagrange multipliers. So I can define some S tilde that's equal to the entropy. So I have minus KB PI ln PI plus lambda 0, some parameter with multiply 1 minus sum of pi plus lambda 1 sum over pi ei minus e plus lambda 2 sum of n pi minus n. So this equal to 0, this equal to 0, and this equal to 0. And we want to find the maximal point of this function. Yeah, okay, just so it's consistent. So to do that, we need to take the derivative s with pi and compare it to 0. So from the first time, we have the derivative of the first one, so ln of pi plus pi 1 over pi, so this is just 1.
Should be all in the sum.
Yeah, you also have the sum basically here outside. Like outside of everything. All of the terms that are going to survive going to include the sum, so we can take the sum outside of the expression. So this is plus 1. From the second expression, I have just lambda 0. From this, I have lambda 1 ei, and from the last expression, I have lambda 2 ni. And all of this is equal to 0. So we want to isolate p1, so the logarithm of pi is equal to minus 1 plus lambda 0 over Boltzmann coefficient plus lambda 1 e plus lambda 2. So pi is equal to the exponent of minus 1 plus lambda 0 Okay, so minus 1 and lambda 0 over k are just, this is just a number. It doesn't depend on the variables of the system like e and I, so I'm going to just define it as, let me rewrite it here maybe. So pi equal to a exponent of lambda 1 so now we need to find lambda 1 and lambda 2, so a eventually going to be a normalization constant. So we're going to add two, not constraints, but we're going to use two known thermodynamics relation, which one is that the derivative of S with energy is equal to 1 over the temperature, and the derivative of S with N is equal to minus mu over the temperature. So this is known. So if you look at like the original equation that we wrote, we can find that. So this is going to give us lambda 1, and this should give us lambda 2. eventually, we take the lambda 1 and 2 that we find and we put it here. So we find that pi equal to a exponent of minus beta ei minus mu n. And then we know from normalization that a is just equal to the sum of e minus beta. We have sum of n and I, and this is not surprisingly what we wrote on the board 5 minutes ago, and that's it. Okay, so this is for ensembles. So remember that for the next tutorial when we're going to add quantum stuff. So everything's going to be much more interesting. Okay, so ergodicity. So you can write like different definitions for ergodicity. So we're going to use two definitions. So the first one, which is it's some maybe a bit more abstract one, but it's the one that we are actually going to use. Okay, so the system is ergodic if any point. Okay, I will just write it and then explain. Okay, so a system is ergodic if any point eventually visits all of the phase space. So I wrote a bit longer definition in the notes, but what basically it means that I have the phase space that defined by all of the possible states that the system can be, and if the system, I start from some initial condition. If the system will, if I let it enough time to evolve, if it eventually will visit each one of the available states in the phase space, it means that it's ergodic. If not, then so one example is so if you have like three gas molecules, so if you let like a particle of gas in a box to just move around, eventually it will visit each point in the phase space of the box. On the other hand, if you have like maybe something like a harmonic oscillator, the motion of the system is constrained to like some specific trajectories, so you're not necessarily going to get to any point that exists. So I'm going to show like in like 2 minutes more concrete example. So just this is one definition. The second definition that is completely equivalent, but this is usually the definition that physicists like to use, which is looking at average. So I can define for some, it's like some measure. So I have some you know, like in quantum mechanics, when you look at like observation values of like the momentum or the position or the energy. So you look at like the kind of the average of some operators. So this can be like the location or the energy or time. So the average can be defined either over time. So this would be usually defined like that, like a line. So I have an integral of a of t dt, and this is like this is not the temperature. This is like the overall time. So just like normalize it.
טליה?
Yeah.
התנאי הראשון זה כמו נשניות בתהליכים סטטיסטיים, נכון?
Yeah, I see. So I can either average over time, and the other option is to average over ensemble. So this is what we actually usually do when we talk about average in like statistical physics. So I have an integral of a that depends on the phase-space coordinates. So I call it like gamma. So gamma is Q and P, all of the possible Q and P's. And then I have the probability density that is rho of gamma and T, which we saw last tutorial with the Wheel equation. And I sum over all of the coordinates in phase space. So this is just usual like statistical average, and this is time average. So if the system is ergodic, we can take the limit of T go to infinity. So A will be equal to, so in the limit where time goes to infinity, the average over time going to converge to the average over the ensemble. So this is if the system is. So if you go back to the free particles, we have a particle in a box. So if we want to talk about the average position of the particle. So one thing that we can do is to just put one particle in a box and follow his trajectory for very, very long time, and then average that. And the other thing that we can do is take many particles and release them in the box and measure the location at some specific time, because this is for specific value of t, and then average over all of the different particles. And if the system is ergodic, which we know it's supposed to be, those two things going to converge to each other. We need to take as many particles and as long the time as we can, and eventually it's going to converge to each other. So this is kind of a bit more intuitive definition for ergodicity. Depends who you ask. So let's look at example. So, okay, before I go to the example, any questions about what I did in the tutorial so far? Okay. So let's look at the transformation that take, so T is a transformation, and it takes X and transform it into X plus 2. This is the system, this is the evolution of the system that we have. So I want to know if this transformation, if that system is ergodic. So basically we have two options. So let's look at the case where the system made of we have like a module 5. So we have like 5 or multiplication of 5. No, multiplication of 5. No. We have 5 sites in the system. So we have 1, 2, 3. And we have some initial condition. So for example, x0 equal to 1. And then we can look at the time evolution of that initial condition. So the particle starts at that position. And then at t equal 1, we have like a discrete time. So for, let's call it n, so n equal 1, x1 is going to be equal to x0 plus 2. So it's going to be equal to 3. So the particle jumps from here to here. And then at n equal 2, it's going to jump from here to here. And because it's modular, we have like a periodic boundary condition. So t equals 3, it's going to jump from here to here. So from 5 to 2, and then from 2 to 4, and then from 4 to 1. So we have 1, go to 3, go to 5, 2, 4, 1. So we can, alternatively, we can take another initial condition. We can start at 2 or 3 or 4 or 5, but you can see that it doesn't matter where we're going to start. We're always going to follow that trajectory because we came back from 1 and then we're going to go back and visit every site from the available sites. So this system is ergodic because eventually we visit all of the phase space. So this is one case. Another case, what happens if we take systems that have an even number of sites? So instead of 5, we take 6. So we have 1, 2, 3, 4, 5, 6. Okay, so if we start with x0 equal 1, so we start here, and then the particle is going to jump to 3, then to 5, and then it's going to jump back to 1, because this is even, and then from 1 to 3 to 5. So we're only going to visit, so it's 1, 3, 5, 1, 3, etc. So we're only going to visit the odd sites in the system. On the other hand, if we start, for example, from x0 equal 2, so we're going to jump to 4, then to 6, and then back to 2, and so on. So here we have 2 go to 4, 6, 2, etc. So if we start in an odd index site, we're going to always end up in an odd index site, and the same with even one. So this system is not ergodic. So in that case, the phase space, we don't have really momentum, but just the possible number of states is just the location on that one-dimensional grid. And we either visit all of the possible sites or we don't visit all the possible sites. So this is very, very easy, relatively easy to see what happens to the system. So if we think about the second definition, when we look at the time and the ensemble average, so we see that like in that case, if I average over time, I'm still going to keep on the same trajectory. Like I'm only going to look at the same one. But if I sum over all of the all of the average, I'm going to sum over all of the possible sides, so it's like it doesn't matter which trajectory I choose. So this will be consistent. So that's for ergodicity.
Yeah.
Yeah.
So it has to go through only on the energy sides in the system, because in the lecture we talked about harmonic oscillator and we have a circle of energy with Q and P, and it doesn't went through all the phase space, only on the circle, because so I don't understand if it has to went through in all the phase space or only in the phase space that there is energy, or
it's all of the available phase space. So okay, so there was, I show you an example. So in the previous semester, there was in the test there was a question. So you have two unknown variables, x and y, and x go from 0 to 1, and y go from 0 to 2. And then you have a given transformation of x and y that I don't remember exactly. I think this is like a sine of x, and this is like a parabolic tan of y. And then the question is that system ergodic. So what you're supposed to do is you say, okay, this define all of the available states that there can be. So you can look at that like Q and P, like it doesn't matter, just two variables, and then define the states, the possible state of the system. And you say, okay, is that expression can go all the way from 0 to 1, and can that expression?
What is the space that you need to cover? You need to cover.
You have like this.
The domain I understand, but
yeah.
What is the image that you need to cover? The same thing, 0 to 1 in the x.
Yeah.
And
so
okay.
this should go from 0 to 1, and this should go from 0 to 2. So this is fine, but hyperbolic tangents have like this saturation thing around 1, so it's converged to, so it's never going to get to y equal 2. So this is not going to be ergodic because this function, just the definition, the function itself cannot get to this point. So you have like very different ways to look at those stuff. Like you can define, like you can look at like more actual physical systems.
What is the name of the function?
Which one?
T. It says a special name or something?
The transformation?
No, this is like transformation.
Okay.
We're going to look now at like a transformation that have a name. So yeah, so we're usually going to look at stuff like that, where like the space is defined like in a very specific way, and the transformation is defined in a specific way, because when you look at like actual physical system, this can become very, very complicated very fast, because ergodicity is actually can be defined through like depend on which variable you're looking at. So like some parameter can be ergodic and some parameter can not be. So this is very complicated. So for us, everything has to be like well defined in that kind of system. So okay, so this is ergodicity. So the last thing before we go to the example and then go home is mixing flow. So you also saw that with Vidor. So just very shortly, if you think about the physical system, we have a difference. Like ergodicity is some constraint of the system, and basically mixing is some stronger constraint of the system. So if I think about the system, so I have a phase space. So this is like x and y, or p and q, and I have some initial condition. So, and this is like t equals 0, and then at some time t larger than 0, the evolution in time can be like this is going to be like here, and this is in even larger time. This is going to be here, and then eventually this time square going to cover all of the phase space. So I have conservation of the volume of phase space, and this is going to cover all of the phase space. So this is a ergodic system, but this is not necessarily a very physical system. So the example that you usually
need to conserve the volume.
Yeah, you always need to conserve the volume.
Okay.
So, because that's actually like rho that we talked about in the last tutorial. So, the example that usually people like to give is if you have if you drop if you have a drop of a dye in water, and then.
But it's not. It depends on time. That means if we will take the derivative of rho with respect to time, it will not be 0, so it contradicts the real theorem.
Partial derivative.
Partial derivative.
You also have.
It will have a dependency on time. That's what I'm saying. Yeah, because it's changed. You describe it. It changed with time. That means you have a change.
Yeah, you can have.
That's mean the partial derivative is not 0 with respect to time, so it's not.
Right, the partial derivative doesn't have to be 0 with respect to time.
So it's not.
Full derivative.
The full derivative is also not 0.
Right. No, full
Because
derivative is 0.
In this system, no.
Because it's maintained the shape.
It's maintained the shape, but it's moving. So
yes,
you have
it's maintained the shape.
time
So technically, it's not supposed to maintain the shape because I want to have change of the coordinates. But for the sake of this example, let's look at it like that. Okay, you can think about something that's go from like that square to like that square, or something a bit more complicated. But just for the general concept, I want to keep it. Okay, so.
But that also will the derivative with respect to time will not equal to 0 in that case.
This is just the full derivative.
The full derivative will not be equal to 0.
So let's look at it later.
Okay.
So yeah, so the example that usually people give is if you have a drop of a dye in water, and then the water are transparent and the dye is like, I don't know, pink. So you have you know that if you put the drop in the water, it's going to mix with the water, therefore mixing. And we don't expect to like mix the water and then come back and see the drop like in a full shape in another place in the cup of water. So mixing is actually what we usually think about like entropy. So this is the thing that's defined like the direction of time. So this is like irreversibility. So we have something that starts in this very like organized form, and with time, so this is without mixing. And this is with mixing. So if we start from something like that, we go to something like, I don't know, like that. You can imagine something that's a bit more messy, and then it's going to, to change with time. So eventually, you're going to have points from that thing that are spread around in phase space and are literally like mixed into the phase space. So the definition of a system that's follow mix and flow is that the correlation between point in phase space, so you have a correlation Cn. Okay, there is a mathematical definition here for those of you who want, but I don't want to write it because it's not present. So this is the correlation function between 2 points in phase space. So when t go to infinity, this go to 0. So if I think about the drop of dye, I have two molecules inside this drop, and if I come back in like 2 hours later, I see that those 2 points are going to be like in very different parts inside this glass of water.
Correlation with covariance. Cn is a covariance.
Correlation.
Correlation, מכניקה.
Yeah.
נכון.
So this is about mixing. So if I come back now, this will be filling all of the. It's look like this filling all of the phase space. So this look may look like it contradicts what we said in the last tutorial about conservation in phase space, because we started from something that has some volume and we added something to fill all of the phase space. So, okay, we're going to see this in the example, but basically what happened is that you can understand that if I think about the dye, the amount of molecules from the dye is like it looks like all of the water are pink, but we know that the amount of molecules didn't change. They're just mixed through the thing, so this is just spread through the phase space, but everything is still normalized. So we're going to see this now in an example. Okay, so Baker transformation. I used to think it's named after a person called Baker, but this is actually the word Baker. So this transformation is defined for, so I have two coordinates x and y. So I'll write the transformation and then we see what it does. So if x is smaller than half, so okay, first of all, both x and y are defined between 0 to 1. So I have this like the phase space is just a cube, not a cube, like a square. So if x is smaller than 1, x go to 2x and y go to y over 2. And if x is larger than half, or let's say larger or equal, define it in any way you want, you have 2x minus 1 and y over 2 plus half. So
you don't have any condition on y?
No. So let's start with a square from with 0, 0 to 1, and let's say I have some shape in the square. Like a happy face.
The image
Something.
should be also in that square? Because I don't think so, unless you have a condition on y, because no?
I didn't choose the transformation yet.
Okay.
This is
No,
just
y
this is
divided
just
to other,
the initial
so,
coordinates. So we can do this transformation by following 2 steps. So in the first one, we do the 2x part. No, okay. In the first one, we take the square and we just press it. So instead of have 1 by 1, we have half on 2. So the smiley face is going to be a bit creepy. So this is like, you understand. So we just smash it to be shorter and wider. And then we cut it in the middle. And we take this half and we put it on top of this half. So how is it going to look? So we have something like that from the bottom half and something like that on the top half. So this is now, it doesn't look like, but it went back to be 1 by 1. So you see that for all of the points that were on that part of the original square, they went to the bottom half. So therefore the y just shrink to the half, and x went to 2x, and everything that was on that part, on that half of the original square, went to the upper part. So therefore you have that shift.
And applying the infinite amount of times will give us mixing.
Yeah. Can you explain again what you just did in this last step?
So, like technically,
Like why?
what? Okay, I wanted to take so this is like I have set of points that's like in red, that each one have like x and y coordinates, and I want to take each one of those points and transform that by that transformation.
Okay.
So the way to do that, because unless you want to go like, I'm not a computer, so I cannot go like point by point and follow that.
Yeah.
So just to explain intuitively what that transformation do, it's I literally I take, that's why it's called baker transformation, because I take it's like the baker take a dough and like smash it, and then you take it to pieces and put it one on top of the other, and that's how he makes the dough. So I take this square and I make it into like a shorter, wider square. I cut this half and then literally just put it on top of this. So
is this like the second line transformation? Like,
yeah, but this is not like the, like how is it? Like this is like yeah, you can say like this is like the first step, because in the first step everyone follows that.
Okay.
And
alright.
in the second step I kind of do that because I just rearrange them on top of the.
Okay.
But this is for like, if you do it like immediately, we go from here to here, so we follow that.
Yeah, I see. Okay. Thanks.
Okay. So of course we can do it again and again and again, and then you can try to imagine. I cannot draw it, but like I can try. But you can imagine that this is just going to be a bit like just going to get like messy and messier kind of plot. So this is the Bacon transformation. You can also define an inverse transformation, which is t minus 1 x and y. That's basically go from that step back to the original step. So here we're going to look at y smaller than half and y bigger than half. So x going to go to x over 2 and y going to go to 2y. And for y larger than half, x going to go to x over 2 plus half, and y go to 2y minus 1. So this is basically equivalent to just replace the x and y. Okay, so first of all, we claim that we want to show that this transformation really conserve volume in phase space. So in the same way that we did in the first tutorial, we want to show that the Jacobian of this transformation is equal to 1.
Which case of x it's 1 because it's
For both.
invertible and
So the Jacobian
not x.
is equal. So let's call the new coordinates x tag and y tag. So in that case, like we have x tag equal to x, and then y tag equal y over 2, and the same for the dx larger than half. So the Jacobian going to be dx tag x, dx tag y, dy tag x, dy tag y. So we have two cases for x larger and for x smaller than 2 because this is basically different transformation, supposedly. So for x smaller than half, this is going to be 2, and then the derivative of x tag with y and y tag with x is going to be 0 because we see that the new coordinates x and y does not depend on the other coordinates. So those diagonal terms are going to be 0, and y tag over dy is going to give us half. Now,
The same thing.
exactly, so for x larger than half, we see that the only change is a shift here of minus 1 and here of half, but the derivative is not going to change. So this is going to be again equal to 2, 0, 0, half. So if we calculate the determinant, the Jacobian, this is just going to be the multiplication of the diagonal terms. So this is 2 multiplied by half, and this is equal to 1. So we do have conservation of volume in phase space. So the last thing we want to do is, because we talked about mixing, if we start with some initial states, so initial probability density in phase space, what's going to happen to it when it go to infinity? So after we apply the transformation again and again and again. So, okay, so we have rho. So rho is the solution of the Liouville's theorem. So this is a density function. So the time evolution, the discrete time evolution, of course, of rho, going to be equal to applying this transformation T on rho at time n, and then let's write it also with, so this is Q and P, this can be also, yeah, okay, let's use X and Y. X and Y. So we can keep applying again and again the transformation and eventually just write that as T n plus 1 on rho n of X and and y, right? Because you just
Rho
apply
No,
zero.
So goes. Rho zero. So this is a density function for two variables. So let's define the density function for one variable. So let's call it phi n of x. So this is the probability to find x within x to x plus delta x. So this is just a density function for x. So this is equal, by definition, to the integral of rho n of x and y dy, where y go from 0 to 1, because this is the given space of the transformation. So we can write that as an integral. No. This one I want to keep, so the time evolution of this probability density function is the integral of t acting on rho n dy so instead of applying the transformation on rho, this is equivalent to applying the inverse transformation t minus 1 on x and y. Because if I have the smiley face in the square that I did before, I can either stretch the smiley face or just shrink the axis itself.
Yeah.
So this is like a relativity thing. So instead of applying the transformation, I apply the inverse on the coordinate themselves. So this is equal to, okay, so if we apply the transformation now, we need to divide the integral into two regimes, one from 0 to half and one from half to 1, because the transformation is different. So from 0 to half, we have rho n of x over 2 and 2y dy plus the integral from half to 1 rho n of x over 2 plus half 2y minus 1 dy. So now, in order to write it in a way that is more convenient, let's use change of variables, but different change of variables for each integral. So here, let's define z is 2y, and here z is 2y minus 1. So this is going to give us, so dz, from the y to dz, we're going to have a factor half for both of them. So I take outside half, integral from 0 to 1, because now the half going to be 1 in the limits, and here the bottom half going to be 1 from this limit. So from 0 to 1, rho n of x over 2 z z, and same from here, rho n of x over 2 plus half So, okay, and now what's that? From the initial definition of phi, this is actually phi n of x over 2, right? Because the integral is the same integral, so the only thing to change is the argument of the function. So this is phi n of x over 2, and this is phi n, well, in the integral of course, phi n of x over 2 plus half. So what we got is the recursive equation for the time evolution of phi n. So we got that phi n plus 1 x is equal to half phi n x over 2 plus phi n x over 2 plus half. So all we need to do now is to solve that. So
Solve that for what? So solve what for what?
we want to find phi n as function of x. So when I say solve, it's not exactly so. So we're going to let's see what we can do. So let's start with n equals 0. So if we take phi 1 of x, so from that we can write it as half phi 0 of x over 2 and phi 0 of x over 2 plus half. From that we can write phi 2 of x as phi 1 and then we can plug in this into that and find phi 2's function of phi 0. So this is also equal to 1 over 4 because we have half from here and from here. And then we have phi 0 of x over 4 and then phi 0 of x over 4 plus half. You don't need that anymore. Then phi 0 x over 4 plus 1 over 4. Then phi 0 of x over 4 plus 3 over 4. Let me some more.
Okay, so the general formula is 1 over 2 to the power of n plus 1. Summing.
So from that we can either see or guess or write the formula and then see if it works. So for general n, this is equal to 1 over 2 to the power n. So this will give us this factor of 1 over 4 and 1 over 2, etc. And then we have summation of some parameter k that go from 0 to n minus the power n minus 1. And then phi 0 of x over 2 to the power n plus k over 2 to the power n. So this is the formula for any value of n, and you're more than welcome to go to higher ends and try to check that. So, okay, so we don't really like summation because we don't really know how to do that. So instead, let's that's why it's an integral, because integrals we kind of better in solving. So there is, okay, kind of the reason that we are allowed to do that is because eventually we're going to take the limit of very long time, and then the n is going to be a very large number, and then the variable that we are summing over, that is k, so this element is going to be very, very small. So this is like going at like infinitesimal,
Just to Riemann sum, right?
just to what?
Riemann sum.
Yeah, so this is just going to be like an infinitesimal change of the integration parameter eventually. So we can say that phi n of x, so instead of summation of k, we're going to go to an integral dk. So phi n of x approximately is equal to 1 over 2n, an integral k.
Don't need the value together.
Just a second. 0 over 2n, and then for that, in order for that to be a bit more valid, we use the change of variables. So let's say k tilde is k over 2 to the power n. So this is an integral from 0, 1 minus 2 to minus n, dk tilde phi 0. So this is the approximate solution of phi n of x. We still don't know what phi 0 is. And now let's take the limit of n go to infinity, because there's nothing else that we can do with that expression. So if n go to infinity, you have to talk louder.
It will approach a constant.
Yes. But before that, if n go to infinity, that means that 2 to the power of n definitely going to go to infinity. So 2 to the power minus n is going to 0. So this expression is negligible compared to anything because x go from 0 to 1. So this is much smaller than the denominator. And also in the limit of the integral we have 1 minus something that is very, very, very small. So this is also going to be negligible. So phi n of x approximately an integral from 0 to 1 dk phi 0 of k. Now the function phi is a density function. That's how we defined it. It's a density function of x. So phi 0, this is a normalized
The average.
density function. Therefore, the integral over all of the density function is just equal to 1. So, what did we do? So we checked the Jacobian of that transformation, and we found that we have conservation of volume in phase space. And then we saw that if we look at the density, probability density, where time goes to infinity, this is equal to the density is equal to 1. So this is actually like uniform distribution through all of the phase space. So, as I said before, this looks like a contradiction because it's I have the density function field over the phase space, but as we said, this is just like the drop of dye in the water, and it looks like it's it's field of the phase space that's actually still going to be be normalized. So this is one example of mixing. You're going to have more examples in the homework. You don't have to go to that level of details, but just so you see some interesting stuff. Okay, so questions.
Why do we have a density function with only two variables inside it, like x and y? Why we don't have a momentum also? Or is it just abstract density function?
It's like as I said, the phase space for P and Q can be like anything. So in the example that I showed initially, you had one-dimensional phase space because it was only the location of the one-dimensional grid. Here you have two-dimensional phase space, so x and y can be whatever I want them to be. This is a transformation that people apply on like different two-dimensional systems. Of course, you can define transformation for higher dimension if you have a more complicated system, but this will be like far too complicated to solve from that perspective. Like those stuff made by mathematicians, so I don't think they solve what specific like physical.
I mean, if density function has only two variables, it means that we are solving like one particle in 1D space.
For example,
It has only coordinate and momentum.
Yeah. Or a particle that, because momentum doesn't have to be the degree of freedom of the system, as we saw. You can have like a model that's kind of an abstract model, like what I showed you, the particle that jump between sides. Well, it doesn't have a defined momentum. You only have one degree of freedom, the location of the particle, so this can describe location of two particles. So it depends how abstract your model is and what you're looking for. Yeah.
That shows that it's ergodic.
It is, but we didn't really show that. Like, yeah, I think we did, right? Because it showed that like eventually it's going to fit or the phase space. So I would say
it's likely to be in each point with equal probability.
Mm-hmm.
That shows that it is.
Yeah, like okay, the definition of ergodicity is a bit like you have you have probability to be in almost every point in phase space. We don't mention the almost because it's not relevant for us. But yeah, you're supposed to have probability to be in any point.
Take a closed small environment, some positive probability to be there, and
yeah, so it's also supposed to be that you're going to visit every point in the phase space infinite number of times. I also didn't mention that, but it means that the probability you have like like a final probability to be in any point, so eventually you're going to get there as many times. So I think this is high enough. So yeah, so tutorial is over.
Why do we also interested in Baker's transformation?
That's about the applications of that?
Yes.
Okay, that's a very good question.
Because it looks like very abstract, you know.
Yeah, so I know that people use it for stuff. I honestly cannot give you like I don't remember the specific applications that people use. I can look it up and we talk about it next time. But yeah, I don't really know. Okay, more questions? No? Okay. Next.
About how it's graded, or is it?
The homework?
Yes.
So okay. So I'm usually